Right, so yesterday we recapped discrete distribution. Now we're interested in our continuous one, so let's actually compare them. So again, I'm starting off with a discrete one here, and it's simply just tossing a coin, or tossing two coins, number of heads that come up. So probability of no heads is a quarter, probability of one head is a half, probability of two heads is also a quarter. So some definitions. Remember, random variable x, our probability function is p of x equals x. Now, the cumulative probability function, which I've called capital FT there, would be the probability that x is less than or equal to t, because it's cumulative, so it's starting at some point and will end at whatever t is. So sum from t equals a to x, if you like, of our probability. So for instance, function 1, our cumulative function, would equal 3/4, because up to that point we have a quarter plus a half, 3/4. Cumulative probability function, another name for it is cumulative distribution function. Okay, now the thing is, for a continuous random variable, the probability function doesn't exist. So all right, let's think of a continuous one and a height of adults. Okay, so between any two values, so the example I've got here, 170 centimetres and 175 centimetres, there's actually an infinite number of possibilities, because you can always keep dividing the measurement down to smaller and smaller and smaller units. So theoretically, there's actually an infinite one. So thus, any particular one, any discrete value, I've just said 172.4, the probability would be 0. Why is it 0? Remember we said yesterday about the histogram, that the area of the histogram gave us the probability. But the width, if we're talking about a continuous one, the width of that rectangle is 0. Therefore the area is 0. It's like saying the integral from a to a. That will always be 0. Let's say there were actually 23 people that had a height of 172.4. But what we're saying is the sample space between 170 and 175 is infinity. There's an infinite number of values in there that they could have. So there's another way of proving that probability must be 0, because we'd say, oh, well, the size of our 172.4, 23, over the size of the sample space, well, I can't sub infinity in, but it'll be the limit as that approaches infinity, again, gives us 0. So if you have a continuous distribution, this is the key bit, the probability of any single value, any discrete value, will always be 0. Now, by using our relative frequencies and placing data into classes, we could come up with one. Classes allow us to do is to treat continuous data as if it was discrete. Because what we're saying is, well, let's just assume every value between 170 and 175 is the same. And so if it falls into that class value, we can give it this discrete number, and we can turn it into discrete. So, waiting time for a ski lift. You've gone skiing, and we've put it into class intervals of a minute in length. So 0, 1, 1 to 2, and so on up to 5 minutes. So relative frequencies are there, and then the cumulative relative frequency I've listed as well. So if we want to find the probability that that waiting time was in between 1 and 3 minutes, well, we can read off our table. There's different ways of doing it. I could just look at the relative frequencies and go, oh, well, it'll be 0.196 plus 0.210, because 1, well, falls in here, and 3 falls in the 0.210, so we get 0.406. I could have used the histogram. So there's our histogram and polygon as well. Now, in this case, conveniently, the widths of each class I made 1, so that makes life a bit easier. So the working out would be the same actually as method 1, because I'm just going to find the area of these two rectangles. And we'll also end up with 0.406. Okay, I could use the relative frequency polygon like I did yesterday, using a trapezoidal rule. And if I use the trapezoidal rule, we end up with 0.40575. So you'll notice not quite the same answer, very close approximation, but not quite the same. I could use the cumulative relative frequencies. So I could say, what's function 3 minus function 1? Well, function 3, if I go back to the cumulative ones, so up to 3, we had 0.620, minus up to 1, that's 0.214, and again we get 0.406. So there's all sorts of ways we could work this out. But what if I said I want to find it in between 1.5 and 2.5? So now I'm going to reduce the class width down to 0.5 so I can do this problem. And so there's now the new relative frequencies and so on. So again, if I use the relative frequencies, probability 0.207. If I use the histogram, but note, my rectangles are no longer width of 1, so I've got to be careful here. So this time I've got to multiply the whole thing by 2 because the width of the rectangles were a half. I actually need them to be 1 to come up with the probability. So I multiply the whole thing by 2. So I get a half times 0.1 plus a half times 0.107, all of that times 2. And again we get 0.207. If I use the polygon, again using our trapezoidal rule, we end up with, well, it's close to 0.207, but 0.20675. And using the cumulative relative frequencies. So, what would happen if we get the width of the class and get it closer and closer to 0? Because ideally, that's what we want to do with our continuous distribution. Remember, we said the width of it is theoretically 0. Well, the area of our polygon, remember at the moment, they weren't the same. But as we get that width closer and closer together, the area underneath the polygon should equal the area of the histograms as that rectangle gets thinner and thinner and thinner. So function B minus function A, if you like. So the difference in the cumulative distribution function. Okay, so where am I heading to with all this? What's called probability density functions. The probability density function, that is the equation of that polygon, right? The relative frequency polygon, as the widths approach 0. It will no longer be a sharp lot of lines like so. It should now become a curve. It will have the properties that function x is always positive, and the integral, so the area under our polygon, going from minus infinity to infinity, so we include every single value, it should be all of the probabilities, because we're saying the area under the curve is the probabilities, the sum of all the probabilities. So it should equal 1. And so if you want to find a particular probability between two values, you integrate that curve, the probability density function, between A and B. Okay, so here we go. Our function in this case is basically we're saying, well look, if x is in between 1 and 4, it's going to be k times 16 minus x squared. Otherwise it'll just be 0. What is the value of k? Well, that's where I'll use integration, because I know this integral must equal 1, going from minus infinity to infinity. I don't have to integrate from minus infinity to infinity, because I know it's 0 otherwise. So I really only have to integrate from 1 to 4. So that should equal 1. Well, let's do our integration. Sub in 4, sub in 1. We get the k is 1 on 27. Find that cumulative distribution function. Okay. Well, the function is 1 on 27. We now know what k is by the integral of 16 minus x squared. So add 1 to the power over the power, sub in x, sub in 1, and we come up with our function. And so we know, because remember it's a cumulative function, so until we get to 1, that value is going to be 0. It hasn't started yet. Between 1 and 4, it'll be this function we've just discovered. But once it goes past 4, that, remember, is where it went to 0. So we're adding 0 on. So it will just stay at the value of 1. So now we want to find the probability that a bid of more than $3 million will be made. So we want to know, when is the probability of x greater than or equal to 3? when we defined X to be the number of millions of dollars that was bid. Well, I'm going to use the complementary result. So I'm going to say 1 minus function 3. And so all I've got to do is sub in 3 into that function we worked out. And there we go, we get 11 on 81. How do we now go and find quartiles? Well, Q1, remember, it's the first 25%. A quarter must be the integral from minus infinity until we get to Q1. The median would be minus infinity till we get to Q2. Well, let's call that M for median. Q3, minus infinity until we get to Q3. That should be 3/4, 75% of the data. So here's our function. We want to find the median of this function. So the integral, well, yes, it's theoretically minus infinity up to the median, but our function doesn't kick in until we get to x equals 0. So we'll be going from 0 to m of a 9th x squared. We want to integrate that, and the answer should be a half. And so subbing in. So our median is a lovely result of 3 on the cube root of 2. So around about 2.38 is the median. How do you find the mode? Well, the mode is the maximum. Because you're going to have a curve. Well, the mode would be the one with the highest frequency. So you want to find the maximum of that function. So in other words, when the derivative is equal to 0 and the second derivative is less than 0. Now be careful, because we're talking about a restricted domain, because it might end up that maximum actually ends up at the end point of the domain rather than a turning point in between. So for ours here, we're going to find the maximum. Conveniently, it's quadratic, makes life easy. Because I don't have to use calculus for a quadratic. I know it's going to happen on the axis of symmetry, and the axis of symmetry is x equals 1. I know the mode's 1 because what I'm looking at here is an upside down parabola. So I know the extremities can't be higher than the vertex on this one. So I don't actually need to check the endpoints. So 16b, play around with this idea.